Okay, so in this video we're going to go over how we can use a polynomial to estimate the value of a function that is not a polynomial. And in our first example we're going to look at the trigonometric function f of x equals sine x. To do this we're going to create a Taylor polynomial, which is just a partial sum of the Taylor series. So you can see at the top of the paper here we have how we're going to do this. We're going to use the index n to add up a bunch of polynomial terms, and then we're going to see how good these are at estimating the actual value of sine. Now you may be thinking to yourselves, I just know the values of sine, I have a unit circle and I've memorized them, and that's certainly true. But I want you to pretend you were an early mathematician who maybe didn't know all of those values, and you were really good at polynomials, and so therefore you tried to estimate these values using something that is predictable, like the polynomial. So let's take a look at number one. You'll need the handout from class to follow along with this video. You can find it on Blackboard if you don't have it. But you'll notice in the table here we've created a series of Taylor coefficients and then a series of Taylor polynomials. So I started out taking the nth derivative in the second column, and then we're going to do technically a Maclaurin series, if you will, by plugging in the 0 here in the derivative. And then those values that I've got in the third column become the numerator in my Taylor coefficient. So you can see them there. What happens for the Taylor polynomial t0 is that we just get nothing, we get 0. But then what I want you to notice is that because the value of cosine 0 is 1 and the value of negative sine of 0 is 0, that our first and our second Taylor polynomials, t1 and t2, are actually the same thing. So even though there's two terms in t1, it reduces to just the line y equals x. And even though there's three terms in the Taylor polynomial t2, it reduces again just to the line y equals x. So here we're saying that if we only take the first and second partial sum, that sine x behaves like the line y equals x. Now if you just try and picture that in your head, you obviously know that's not true. But it may be true if we look just at what sine's doing near 0, where we've decided to create these Taylor polynomials. All right, if we move down, looking at the Taylor polynomials t3 and t4, we get 4 and 5 terms, but because of the zeros, both of those Taylor polynomials turn out to be x minus 1/6 x to the cubed, x cubed. I just evaluated 3 factorial as 3 times 2 times 1 to get that denominator there in the 1/6. Now again, if you're good at polynomials, you kind of know the curve or the shape that this guy's going to take. It's going to kind of have one peak and one valley. It's going to go down on the right and up on the left because the leading coefficient is negative. And again, the end behavior certainly is not the same for this polynomial as sine x's end behavior is. It's certainly, this polynomial is not bounded by -1 and 1. But maybe near 0, it might look like sine, and we might be able to use it as an estimator there. All right, finally, looking at t5 and t6, lots of terms there, but also lots of terms cancel out. And we end up with the same fifth degree polynomial to estimate sine, and that polynomial is x minus 1/6 x cubed plus 1 over 120 x to the fifth. And again here, I evaluated 5 factorial to get that 120 in the denominator of that coefficient. All right, so knowing what we know about polynomials, this guy may have more than one peak and valley, but it should be going up on the right and down on the left. So not very similar end behavior to sine x, but perhaps good behavior in the middle. So we're going to take a look at two angles, one angle that's kind of close to 0 and one angle that's a little further away. And we're going to see how they do in our Taylor polynomial. So in number 2, let's imagine that we want to look at the angle or the x value pi over 4. Now pi over 4 is generally close to 0, but not entirely that close, and pi over 2 is a little further away. Now, of course, as I mentioned before, you know the sine of pi over 4. It's just the square root of 2 over 2, or approximately 0.707. You also know the sine of pi over 2 equals 1. So you do not need a Taylor polynomial to figure out these values. But again, I want you to imagine that you maybe didn't know that, and you knew that you could plug things into a polynomial and see what they gave you. So we're going to take that pi over 4, that x value, and plug it into t1 and t2, that line we found, that line y equals x. Well, if that's the case, then we just get x, and x is just pi over 4. If you put pi over 4 into your calculator and get the decimal approximation, it's about 0.79. So, you know, we're off here in the 100th spot, so not a great estimate. But let's see what happens if we plug it into T3 and T4. So remember, T3 and T4 are actually the same polynomial, the cubic polynomial. We're plugging in pi over 4 for x, and you can see we start to do a little bit better for pi over 4. We get to about 0.705, which is better. It's closer to 0.707. We're off there in the, what is that, thousandths spot? So perhaps if we do a larger Taylor polynomial, T5 or T6, we might do better. So plugging in pi over 4 to T5 and T6, up to that third decimal place, it appears that we've done it. Now, of course, I'm only rounding to the third decimal place. If you were to get your calculator out and look further on, you'd see that it's not exactly the same. But if you needed something that was within that range of error, then you could use that polynomial and you would get a pretty good estimate. Now, what we'll notice is that the estimates still improve for pi over 2, but they don't get quite as good. And we'll kind of look at the graph to determine why, but oh, I have a typo on there. Hold on. Do you see this typo here? This guy should be pi over 2. My bad. Okay, so when we do pi over 2, we're going to do a little bit worse because pi over 2 is further away from 0, and 0 is what we use to create the Taylor polynomials. So we know sine pi over 2 is 1. So if you just do x, that line, you get 1.57. That's not good at all. But if you plug it into T3 and T4, you get a little bit better. You get down to 0.925. We're trying to compare that to 1. And then if you fix my typo over there, pi over 2, plugging it into T5 and T6, we do a little bit better, 1.005. Not quite as good as the estimate for pi over 4, but that's because pi over 2 is kind of further away from the center point, that a equals 0. So we've summarized that down here in number 3. Sorry, got a little shaky. And you may notice that, you know, we do better with the bigger polynomial. We still do better with pi over 2, but not as good. Pi over 2 is further away from 0. But the bigger the Taylor polynomial, the better the estimate. So we're going to kind of look at these guys now in the calculator. So I'll show you how I set up my calculator. I went ahead and put the function that we are trying to estimate here as sine, and then my 3 Taylor polynomials, and then I want to kind of look and see what they're going to look like. Ooh, spoiler alert. Okay, so there are my polynomials in there. I'll show you my window. I did negative 2 pi to 2 pi, and then I did negative 4 to 4 for y. And then, oh, can I make a graph again? Let me see if I can get it to graph fresh for you. Okay, there we go. Here it's going to graph sine, should look familiar. A line, not great, except at near the origin. Cubic function, again, not great, except near the origin. And our quintic, or our 5th degree polynomial. Pretty good near the origin, not good far away. So where you decide to take your Taylor polynomial, that a value is going to tell you where you can get the best estimates. Now imagine I tried to use these guys to estimate 2 pi or negative 2 pi. They'd be terrible. They'd be giving me some infinitely large number, which of course we know is a terrible estimate. Sine of 2 pi and sine of negative 2 pi is 0. So it is important to pay attention where you've centered your Taylor polynomial so that you pick reasonable values that that polynomial can estimate.